Hello, Astronomy. Welcome to our first video lecture for Unit 3, the Tools of Astronomy. So let's take just a second to sort of see where we've already been in the course. So in Unit 1, we did what is astronomy. We talked about how the sky works, how ancient peoples viewed the sky, things like the zodiac, things like retrograde motion. Unit 2, we did a bit of a history lesson with the birth of modern astronomy that eventually got us to the heliocentric model, the actual, understanding of how the solar system works. Unit 3 is called the tools of astronomy. In Unit 3, we're going to keep going even further. So 3 is going to be sort of a deep dive into some physics, which we need to understand how we can learn, how we can observe things in the sky. And I don't want to get too metaphysical right now, but this first video is very important to me that we do some of this physics, because there's a lot of things that we can learn from the sky, learn from space, and by extension learn about just existence itself by studying radiation. Right? The ultimate goal of science is to understand the world around us. And this class is astronomy, so we're understanding things in space. But these sort of tenets of physics that we're going to go through in this first video really help us understand what existence is. So we're going to get a little bit meta, but that's okay. We can handle it. Okay, so let's jump right in. So in this picture, you can see there are 3 different ways of transferring energy. There's conduction, there's convection, and there's radiation. So this is a person holding a pot of water over an open flame. Conduction would be transferring energy, in this case heat, from solid to solid, so from the handle of the pot to the person's hand. Convection is transferring energy through a liquid or a gas. So in this case, the heat's going through the air and it's heating water, which is a liquid, obviously. Radiation is when energy gets transferred, in some cases, through the vacuum of space. So when you don't need a medium to transfer the energy, conduction, the medium is a solid. Convection, the medium is a liquid or a gas. Radiation, there is no medium. And radiation is what we use to study things in space or on Earth too. So the reading talked about famous Isaac Newton experiment. He's the guy that figured out that white light was actually multiple colors by putting light through a prism. He also, to prove that the white light was made of the colors, he was able to configure this to where you put the rainbow back through a second prism and you got white light back out again. So when you separate light, whatever light is, it separates into the colors and then it combines into white light. All right. The idea of Roy G. Biv, red light being on one end, violet or blue light being on the other end, comes from Newton. Roy G. Biv, that's 7 colors. There aren't 7 colors. There's really an infinite number of colors. Okay, so one thing Newton also did, so like when you take, say, red light and put it through a prism, you don't get colors. It's still just red light. So whatever red light is, it's one of something, and it will bend, like the prism, in this case, red or blue light, the prism bends the light. If you bend white light, you get the rainbow. When you bend blue light or red light, you still get the same color. It just changes its direction. So the next famous experiment was by a scientist named Herschel. And Herschel discovers infrared radiation. So he, you take light, put it through a prism, put a thermometer in each color of the prism from blue to green, all the way to red. And the thermometer will go up because, light as energy, light will heat stuff up. Well, Herschel put a thermometer in the space next to red where there was no light, at least that you can see, and the temperature still went up. And he called that infrared. Infra means beyond, so it was beyond red, so infrared, beyond red, that there's still something there that the prism is separating out that does cause the temperature to go up. On the other side of violet would be ultraviolet. Right, other side of red would be infrared. So let's take a quick aside into the electromagnetic spectrum. So I know you've covered this in middle school, you've taken physics, you've covered this before. So the EM spectrum is basically all of the wavelengths of light given off by the sun, all right? Visible light, what we can see with the naked eye, is just one little narrow sliver of the EM spectrum here. On the left-hand side, this is the shortest wavelength. On the right-hand side is the longest wavelength. So short to long, gamma is the shortest. Gamma radiation, that's how the Incredible Hulk became Hulk, right? It will mutate your DNA. And as you're getting longer, this side's still pretty short. X-rays go through muscle tissues. They don't go through bone. So that's how you get an X-ray of yourself. X-ray exposure can mutate your DNA too, can cause cancer. Then you have ultraviolet or UV. UV can mutate DNA. It can cause skin cancer. It can burn you. Then you have visible light. So then going to the right after visible light, which we'll come back to visible light in a minute, you have infrared waves, IR, which is that's what you give off. It's body heat. This doesn't show microwaves. Microwaves are next. And then you have radio waves, which is just showing multiple kinds of radio waves, which is the longest part of the spectrum. So common test question is put them from short to long: gamma, X-rays, UV, visible light, infrared, microwaves, then radio waves. The short side of the spectrum can be very dangerous. The long side, like radio waves, are harmless. Radio waves go through solids without much problem. Although if you're driving through a cave or a tunnel and your radio cuts out, it's because radio waves can't go through any solid. But if all the doors and windows in my house are closed, if I have the radio turned on, obviously you can still hear the radio. So this is showing a zoom in on visible light. So these numbers, 400 to 700, these are in nanometers. So a nanometer is a billionth of a meter. So there are a billion nanometers in a meter. And the numbers, 400 to 500, 600, 700 are much easier to say than talking about billions of a meter. So when we discuss visible light, we're talking about nanometers, all right? So look at the numbers. So if there's a ray of light hitting your retina that's 400 billionths of a meter, 400 nanometers, your eye says that's purple. If it's 530, that would be green. If it's 570, that's toward yellow. If it's 700, that's towards red. So the difference here is only 300 or 400 billionths of a meter as to how your eye separates the colors of the rainbow, all right? So what color actually is it's the wavelength, all right? Color is wavelength, wavelength is color, right? Your eye in your brain takes the wavelength and then your brain turns it into a color. So without eyeballs and brains, there is no color, there's just wavelength. What part of the EM spectrum would it be if it was 1,000 nanometers over here? That would be infrared, which you can't see because your eye can't detect it. What if it was 100 nanometers over here? That would be ultraviolet, okay? So again, visible light is just the part of the EM spectrum that your eye can detect, your brain can interpret. If you could see infrared, you would see body heat. Some like pit vipers, some animals can see infrared. You obviously cannot. Okay, so this is an interesting graph. So this is showing the sun, the light going off by the sun. The wavelengths here are in nanometers, right? So this is looking at the sun outside the atmosphere. The atmosphere blocks and scatters and absorbs. It screws with the light, right? So if you're looking at the sun from space, the sun's radiation peaks at, actually it's green toward yellow. Our eyes are not as sensitive to green as they are to yellow, which is why the sun looks more yellow than green. Although in space, it just looks white. If you look at the sun in space, this is a picture from the space station, the sun looks white because again, your eyeball combines all these colors to show white, but the sun actually peaks in the, we'll say greenish yellow part of the spectrum, right? Does the sun give off violet? Yes. Does it give off red? Yes, but it peaks at green. Let me go back a second. One thing that I meant to say, just clear one thing up. This end of the spectrum, we call it the red side, the red end. That's the red end. it has longer wavelength, shorter energy. So this side of the spectrum is longer wavelength, less energy. This side, we call it the blue end. I know purple is actually the end, but we call it the blue end. This side of the spectrum would be shorter wavelength and higher energy, all right? So the sun's peaking in a region of the spectrum towards the middle. Red light has less energy, longer wavelength. Blue or violet light has shorter wavelength, more energy, okay? But notice how you get a spectrum. And obviously the sun gives off infrared too. It gives off a lot of heat. That's not surprising. But it's not peaking there. It peaks. And actually, our eye is most sensitive to yellow. And that's more or less where the sun's peaking. And of course, if you look at this through the atmosphere, the atmosphere scatters more of one wavelength than others. So what gets through the sun to us the most is actually yellow. And our eyes are most sensitive to yellow, which just shows how human evolution's made us very well adapted for what's getting through the atmosphere. Anyway, I'm getting off topic. Here you can see the peak solar radiation coming from the sun is in green, greenish yellow. And here in space, the sun looks yellow. The sun looks white because it's giving off all the wavelengths. Okay, so like I said, what color is? Color is wavelength. Wavelength is color for visible light. And the wavelength tells you the type of EM wave. So radio waves have this wavelength, gamma radiation is this wavelength, blue light's this wavelength. We classify what type of wave it is by what the wavelength is. If it's color, again, we use nanometers. Okay, so I'm going to move my face so you can see this whole slide. So this is something I want to read to you this word for word because this gets into something of a fundamental property of matter and things in space. So let me first just read this to you. Since all matter is in constant motion, all objects emit thermal radiation. The question is, what wavelength does a given object emit? All right. So thermal radiation is the radiation, the energy of movement. All right. Even if you're motionless, right? Your blood's moving, your atoms are moving. If there's molecular or atomic movement at all, there's thermal radiation. And I have a note here, even at absolute zero is negative 273 Kelvin. It's when all molecular motion stops. So, you can kind of simplify that as there's no thermal radiation. Even on the quantum level, there's still movement. We're not going to get into that whatsoever. But the point that I want you to take from this is that because matter is in constant motion, even in a solid, the atoms are vibrating. There's thermal radiation. That radiation could be visible light, it could be infrared, it could be UV, it could be gamma, it could be X-rays. The question is, what wavelength are you personally giving off? All right. And to do that, we're going to discuss a law called Wiens Law or Wiens Law. So this was named for a German guy named Wilhelm Wien. So this is German. W's are pronounced with V's. So he said his last name Wien. I've heard this pronounced just as often Wiens Law because English people can't pronounce German words correctly, I guess. So Wiens Law. I've heard it Wiens Law more than Wiens Law, but I feel bad for the guy because he would have said Wiens. Germans would call a wagon, right? Okay, so this is a law called Wiens Law. And the law says the type of radiation given off by an object does not depend on what it's made of, but only on its temperature. This is not intuitive. The type of radiation given off by an object does not depend on its composition, but only on its temperature. So it could be lead, it could be gold, it could be rock, it could be chair, it could be anything. The radiation that it emits is only a consequence of its temperature. And now if all objects emit thermal radiation, why can't we see it? Well, we only detect visible light, right? Wiens Law is super important. You need to know Wiens Law like word for word. Wiens Law has a formula. We're not going to do actual math. I'm not going to actually have you plug in numbers, but I do want you to memorize what the formula is so that you can understand how to use it. So I heard this once described with this idea of all objects giving off thermal radiation is that basically all objects glow. All objects glow or emit some kind of radiation. More often than not, it glows in infrared, which is our body heat, right? Which means obviously we cannot see it, all right? So equation for Wiens law. So this symbol stands for wavelength. So the maximum wavelength, if we're talking about the sun, the maximum wavelength is this one right here, right? The maximum wavelength equals this 0.0029 is a constant. The km are just the units for the constant. As long as you're using the wavelength in meters and the temperature in Kelvin, that's the constant to use. But basically, you just you divide, excuse me, 0.0029 by the temperature in Kelvin. Now the temperature is in the denominator. So as the temperature gets bigger, as it gets hotter, the maximum peak wavelength goes down. All right, now we've already said as the wavelength gets smaller, like from red light to blue light, as the wavelength gets smaller, the energy goes up, right? And of course, higher temperature, more thermal energy. So this just goes to show if T gets bigger or something gets hotter, the max wavelength goes down. If T gets smaller, if an object cools down, the maximum wavelength increases, okay? So again, I want you to have this equation or this formula memorized so that you can explain to me, like in a short essay, what Wiens law is. And of course, what Wiens law does is it tells you what wavelength objects emit at based only on their temperature. Another way to say that is the higher the temperature, the more radiation is emitted, and the shorter or bluer the wavelength of the bulk of the radiation. Now again, like if you're in X-rays and you go toward gamma, like that's getting shorter. Is that actually getting bluer? No, we say blue for short and red for long, but that can be a little misleading depending on where you are. But the higher the temperature, the more radiation you give off of a shorter wavelength, which means it has more energy, okay? This is a picture. So this is a gentleman. He's holding a trash bag. Notice he's wearing glasses. So the picture on the left is a visible light picture, like it's black and white, it's visible light. You can't see his hands because there's a black trash bag that blocks light, right? You can see his eyes. Now there's glasses that between his eyes and the camera, but glasses don't block light. They wouldn't be very good they might be good sunglasses. They wouldn't be good glasses to correct your vision if light can't go through them. This picture is taking using an infrared camera. So it detects heat. Heat does not go through glass very well, right? So you can't see his eyes. Heat will go through a trash bag just fine. Right? You put something hot in a trash bag, it gets hot. So you can see his hands, and you can see his skin is sort of glowing because he's giving off body heat. Here you can't see his skin under his shirt because the shirt blocks it. Here you can see, excuse me, the infrared because heat will go through your clothes. So this leads to a very important consequence in astronomy, and that is if we can only detect visible light, we are severely limited in what we can study, all right? This is a picture, this is a nebula, it's called the Pillars of Creation. It's a very famous nebula. These are both Hubble telescope pictures. This is with visible light, this is with infrared. Notice in this picture, you see these massive plumes of gas and dust. Can clouds block light? Absolutely. Clouds can block light. You can go outside, you see a cloud, you can't see through it, right? If we limit ourselves to visible light, we can't see inside the nebula, we can't see through the nebula. But if I have a camera that can detect infrared, I can see through the gas cloud. This is a huge deal, people. Like I can see inside the cloud and I can see stars that are behind the cloud because their visible light gets blocked, but the infrared light does not. So in space, if I can study the entire spectrum, if I have cameras that can detect X-rays, visible light, infrared light, ultraviolet light, radio waves, microwaves, you name it, that I can see way more than what the naked eye can see. You can literally see inside things, or in this case, through things, by studying other parts of the EM spectrum, okay? So this is a nebula called the Crab Nebula. We're gonna see the Crab Nebula, I believe, later. This is taken, I'm not quite sure what this how this picture's taken, but you can see at the bottom, and they've added the color. This is a picture using radio waves, infrared, optical, just visible light. This might be a comma. Anyway, ultraviolet, X-rays. Now again, X-rays aren't purple. Like they've colored these pictures to highlight things, but you can see in each of these pictures down here that the nebula, excuse me, the nebula looks different. You can see different features of it because you're looking at different parts of the EM spectrum. This is a quick little video. I'm going to play this Crab Nebula. This is just kind of cool. There it is right there. And notice inside the nebula, there are stars, there are filaments, dust, stuff. Anyway, I just thought that was kind of a cool little animation. Okay, so I want to make a quick distinction about color and glowing. So this is a blacksmith who's heating up a piece of iron, I assume. So this piece of metal is glowing red. So okay, so say you have a red apple, right? What kind of thermal radiation is that red apple emitting? All right, well, the apple looks red because it reflects red light from the sun or from lights, all right? The apple is not glowing red. What color is the apple glowing? Well, the apple surface temperature, say it's room temperature, things at room temperature glow infrared. So the apple emits infrared. Pretty much any object that it's in a classroom, besides lights in a computer screen or a light bulb, most objects around you are emitting infrared, all right? Now, this piece of metal is glowing because it's gotten so hot, in this case, 11 to 15 Kelvin, 1500 Kelvin rather, that it's glowing red. So emitting red or glowing red is when you actually give off thermal radiation that's red. If something just looks red, like the red apple, is because it's reflecting red, right? If your textbook is red, it reflects red, but it emits infrared based upon its temperature. So this is a very famous schematic of Wiens Law. So let's go back. So let's say that this piece of metal is 1500 Kelvin. So each of these peaks is a temperature. So this is the peak for 6000 Kelvin, which is about the sun's surface. The sun's surface is between 5 and 6000 Kelvin. Its peaks around yellow, right? If I go down to 5000 Kelvin, that's a less temperature. Notice you've shifted it a little bit toward the right, which is longer wavelength, right? As these peaks get lower, in terms of their temperature, the peak, see this line right here? The maximum wavelength is being shifted towards the right. Now, this piece of metal was glowing at 1500, so this is the curve for 3000. Imagine one for 1500, it's gonna peak way down here. So it's gonna peak in infrared. So this piece of metal is very, 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 very hot, right? No one would doubt that. You can't see the peak, but what's the highest color of visible light that you can see? It would be red, right? So as objects get cooler, say from the sun down to a glowing piece of metal, the maximum wavelength gets shifted towards the right, or in this case, towards the red end. Is this thing peaking in red? No, it's peaking in infrared, but the highest visible that I can see is red, okay? As this object cools down, it might turn yellow then orange, or actually will turn orange then yellow, because as it cools down, no, actually I said that wrong, erase that. As that object heats up, it might turn more orange to yellow, maybe even to white, because if it's white, you're getting enough of the colors where they combine to appear white. But as it heats up, you're getting a higher peak, say in the orange or yellow part of the spectrum. So again, what Wiens' law is saying is that the thermal radiation, the maximum wavelength that's emitted, is only a consequence of the object's temperature, all right? The temperature tells you what peak it is, and it varies by wavelength, or the temperature varies with the maximum wavelength is. Okay. This is another visual of Wiens Law. The colors of the line are what the peak is. So here it peaks in green, here it peaks in yellow, here it peaks in orange, and then we're getting toward red. You can see as the temperature goes down, the peak moves towards red. So as temperature goes down, there's less energy, and it gets shifted towards longer wavelengths, which is red. Okay. Okay, so we're going to end with this slide. We're going to end with a mystery. We're going to end with a tantalizing fact about the cosmos. So of note, I'm going to read this to you word for word. This is huge. The entire universe emits a thermal spectrum of 2.7 Kelvin, which responds to or corresponds to a peak wavelength in the microwave area of the EM spectrum. This is referred to the cosmic microwave background radiation. So this was discovered in the mid-20th century, I believe. The story of how this was discovered, it's a very fascinating story. The guys who discovered it won the Nobel Prize. Bird poop is involved. We'll get to that later. So if I point a microscope, telescope, or a microscope detector just at any point in the sky, so don't point it toward the sun because the sun interferes. Don't point it toward Mars. Mars interferes. Point it to a blank part of the sky where there's nothing there that you can see. Everywhere, everywhere, the entire heavens are bathed with a thermal spectrum in the microwave region. There's microwaves, right? We give off infrared. Space is bathed with thermal radiation that corresponds to 2.7 Kelvin. Okay. The wavelengths of this picture, here the wavelengths are in centimeters. Previously, we did wavelengths in nanometers. So here we're in centimeters. And that peak is 2.725 Kelvin. All right, which that's microwaves. Remember, we can relate the type of wave to its temperature with Wiens Law. What the heck is this? Like, we are continuously, we're living in a bath that surrounds all of us, and all of space is living in a bath of 2.7 Kelvin. We're living in a microwave soup of 2.7 Kelvin. Like, it's the same that way or that way. Like, what the heck is this? How can we explain cosmic microwave background radiation? It's there. It's like being in the ocean and trying to explain the water. It's all around us. All right, we're always surrounded by, there's no beginning or end. Well, the ocean, there's a beginning or end, but if you're in the ocean, you can't see a beginning or end. Anyway, so what this actually is, I'm going to save this for a later video, but for right now, just be tantalized, just speculate on where this cosmic soup of microwave background radiation comes from. And on that note, we're going to end it. I hope that was helpful, and I will see you guys next time.